Hello from Intellipaat, guys. I am a trainer at Intellipaat, and today we are going to be going over big data on AWS with this particular workshop. So, the technologies that we are going to be discussing today, specifically on the AWS platform, is EMR. So, let us go through the agenda actually to get an idea of what we are going to understand today. So, firstly, the agenda is quite simple for today. We're going to just go over a brief introduction to big data. Now, so those of you who are absolutely new to big data, before you actually get into the cloud platform, which is AWS, just to give you an idea of what big data is, because big data is sort of different from data. So there is a difference. We're going to discuss what that difference is. Then we're going to understand what Hadoop is. Now, Hadoop is a fundamental aspect, fundamental framework on which big data is computed and stored. So we're going to understand Hadoop. Then we're going to understand a relatively newer technology for big data that is sort of based on Hadoop, but it's not exactly Hadoop. It's called Spark. We're going to understand the advantages of Spark. Then finally, we're going to understand what technology we are going to be implementing today, which is Elastic MapReduce or EMR on AWS. Then we're going to get to the hands-on section where we are actually going to be solving a Facebook data set. Essentially, we're going to be performing some big data operations on a Facebook data set and answer some of our queries from that. So let us begin. So firstly, what is big data? This is the first question that comes up, right? And big data essentially is described as something that qualifies these five criteria, right? So there's a difference between data and big data. Data can be structured, semi-structured, and unstructured in nature, right? So say, for instance, the SQL tables that you have in MySQL MySQL databases or Oracle DB databases, those are SQL tables, proper columns, proper rows. So that is called structured because it has an order to it. Everything about that data set is structured in a way, and you can access any information from it. You can compute it very easily. It's optimized in a way, right? So it's called structured data sets. Then you have semi-structured data sets, which are essentially files in which there is some sort of a structure, like there's a format to which data is written on those files, right? But the thing is, they are not arranged in the format of SQL tables properly organized, right? So you'll have to convert semi-structured data into structured data. And then finally, you have unstructured data, which is just random combination of files. Like say, for instance, you have video files, image files. So if you convert them into text files, you basically get random information. So that those are called unstructured data sets, right? So big data is essentially based on the concept of data, and the five criteria that need to be satisfied for data to be considered as big data. These are called the five V's of big data, right? So these are velocity, volume, variety, veracity, value. So velocity means that data should be coming in continuously, right? It could be coming in every hour, it could be coming in every second, it could be coming in every minute, or it could be coming in every day. But whatever selection is there for the data to be coming in, it should be coming in extremely large velocity, right? So say petabytes of data coming in every day, right? So that accounts for big data because you're generating and storing petabytes of data every day. So that is a very high velocity. Then obviously the most obvious thing about big data is volume, right? So volume means that the data should be enormous in size as well. It should take a lot of disk space. So this could range anywhere from the higher amounts of gigabytes to terabytes to petabytes. So that satisfies for big data. Although today, these days, gigabyte does not count in big data because of how cheap storage has become. We do not consider GBs big data anymore. We only consider terabytes to petabytes big data. Then we have variety. So variety essentially means that the data should be coming from heterogeneous sources. So for instance, if you're working in a company like Amazon, right, as a data analyst, so in Amazon, there are teams. There is a sales team. There is the sort of the team that maintains the user databases. So there is a user database and a sales database. But for an individual who's working at a higher position, he needs to see all of this data aggregated, all of this data together, right? So he will combine the sales data and the customer data. He will combine all of that and see it in one view itself. So when those data sets are combined, essentially, those are coming from two different sources. and they are combined. It accounts for variety, right? So that is also a key factor for big data. It could also be that files coming in of different formats. One could be coming in as a CSV file, one could be coming in as a text file, one could be coming in as a JSON file. So that is variety. Then there is veracity. So veracity means that the data cannot be perfect, right? So every data set that is that big in size, like terabytes to petabyte in size, wherever it is collected from, it will always have mistakes, it will always have noise, it will always have missing values, it will always have inconsistencies. So the data will not always be perfect, and it will not always be representing accurate values. Like some users on Facebook might be creating fake accounts, right, with fake age, fake gender. So if we take that data, we have to account for a certain amount of inconsistency in that data. So the data cannot always be perfect and true. So that is veracity. Then we have value. So value means whatever data you are actually taking, no, doesn't matter if it's perfect or not, it should have some value when we are actually using it to create a big data model, we are actually using it to analyze some big data, or we are actually using it to create machine learning models or artificial intelligence models. The data should have some value. So say for instance, universities have academic data sets, right? So there is a column for roll number, there's a column for name, there's a column for grades, right? So we are concerned with only the grade column and maybe the name column. We're not concerned with the roll number column particularly, right? What will we do with the roll number column? We cannot actually compute the merit of any student with the roll number column. It's just random data. So that particular column is not of any value. So we only have to take data that has some value associated to it. So that is called the value criteria of big data. So these are the 5 V's of big data, and any data set that satisfies these 5 V's roughly is can be considered big data, right? So let us continue with that. So I have a question here. Are these 5 V's compulsory, or if one of the above V's is satisfied, can be considered big data? So as I said, they have to be roughly satisfied. So all of these criteria, there's not a fixed threshold for that. If we are talking about velocity particularly, as I said, it could be coming in days, it could be coming in months, it could be coming in not years exactly, years would be too much. That means that there has to be a certain amount of pace associated with that data that accounts for such a volume that's extremely large in size. So in reality, big data is so huge. When you're talking about terabytes to petabytes of data, it is so huge that all of these 5 criteria will generally be satisfied, right? But yes, if you have to call something else, something that does not satisfy all of these criteria perfectly big data, you can call that as well. But these are generally what you have to base your idea on. So essentially, these 5 criteria need to be satisfied in a way. So let us continue with that. Now, where we have the idea of what big data is, right? There are a lot of problems associated with big data as well. So we get to the introduction to Hadoop. So we're going to be solving those problems by understanding what Hadoop is, right? So big data obviously has a lot of issues when it comes to computing it, when it comes to storing it, right? You cannot store big data on a normal computer that has a 1 terabyte hard drive. Obviously, if the data is above 1 terabyte, you cannot be storing it on a 1 terabyte hard drive. And even if you manage to have a combined hard drive of say 5 to 6 terabytes, and you're storing that data on it, right? Then what will happen is, what happens when you try to process it? It will take days, right? If you try to process terabytes of data on your computer with a single i7, even i7 CPU, it will take days to process that amount of data. So the alternative to that would be to actually have a lot of computers combined together. So we'll get to that. Apache Hadoop is a platform used for storing big data across a spectrum of devices. So instead of one device, Apache Hadoop as a platform comes in. It's a framework that allows you to combine multiple devices together using LAN wires, right, or network. You combine the multiple devices together and you store that data across those multiple devices instead of just one device. So this is this is useful to process this big data and store this big data in parallel. So that means that you divide the data into a certain amount of parts, right? And then the data is processed in parallel. So each computing device will process that block of data that it has been assigned. So that is what it means. So when you compute all of that data in parallel, you drastically reduce the time in which the data can be processed. So it is made up of distributed file system called HDFS, which is the Hadoop distributed file system, and a computation layer called MapReduce, which is Hadoop's processing framework. So HDFS stores the files and MapReduce processes the files. And Hadoop is open source. So obviously, if you want to tinker with it, if you want to add some upgrades to it for your own use case, you can easily look into the source code of the Hadoop framework and edit it according to your needs as well. So let's continue. Let us look at the HDFS architecture. Now, follow me here. Basically, HDFS is comprised of the name node, data node architecture. So what does that mean? Say in your Hadoop cluster that you have created to store and process big data, you have combined 8 to 9 computers. 9 computers. Let us assume you have combined not 9 computers, 4 computers you have combined, right? So you have connected them through LAN wires. You have created your network. So the computer with the weakest specifications, with the weakest processor, with the lowest RAM, with the lowest hard drive space, you will assign as your name node in Hadoop. And the computers with decent specifications, you'll assign as data nodes. So one you assign as name node, and the rest of the remaining 3 you assign as data nodes, and you connect them all together, right? And Hadoop is installed on top of them. So when you come in and try to store a 5 to 6 terabyte file, right? You come in and try to store that. What will happen is the moment you as a client, as you can see my mouse over here, right? So you as a client, you try to access this Hadoop server that comprises of these 4 nodes. You will contact the name node and you'll say, I want to write a file of this 3 terabytes, this big data file of 3 terabytes onto this Hadoop cluster, which comprises of these 4 nodes. So the name node will then check all of the data nodes. It will check all of the data nodes. It will look for the space present on these data nodes, right? And it will look of the status of these data nodes, whether they are active or they are not active. Once it has determined all of the specifications and the status, it will then divide that file into parts, into blocks, right? So these blocks, you can determine the size of these blocks by specifying in the configuration, but it can be around 120 MB at an average. You can specify blocks. So what this particular name node will do, it will divide the file into the block size, as many blocks as possible. And then it will start distributing those blocks across these data nodes, 1, 2, and 3. And in a relatively proportional amount, depending on the space these data nodes have, it will distribute them and store them on those data nodes, right? The name node will store the metadata of this data as to what part of the block is there. So the part 1 is on, say, data node 1, it will store that information. The part 2 is on over here. The part 3 is on over here. Name node has all of that information, right? So it will do that. Then what the data node will do is it will replicate those blocks across all of these, depending on the replication factor, it could be 2, 3, 4. Depending on how many times it has to replicate those blocks, it will replicate it across these data nodes. So replication is done to prevent any sort of data loss. So if you store only one copy of the block on one data node, what will happen is if one of the data node fails, right, you lose that block permanently. You don't want that. You want to replicate it across the data nodes. So even if one data node fails, you still have a backup of that data, right? So you replicate it across, depending on the replication factor, you replicate it across those data nodes, and you have your file stored on the HDFS server, right? You have a very big file, a 6 terabyte file stored across this entire server, right? Without any issues, without any particular data node having to store a lot of data. You have divided it very specifically for that purpose only. Then say a HDFS client wants to read that data, right? So he'll try to access the name node again, right? He'll ask, where is this file? The name node will tell that client the file is present. The first part of the file is present on this particular data node. The second file is present on this. Third part is present on this, right? And the best thing about the data replication is that the client will read the files that are closest to him. So from a latency point of view, from a closeness of a device point of view, where there is the least latency involved. The client will fetch that data from the least latency causing data node, right? So the closest block that he has, he'll fetch it from this data node. Even though this green block is over here, the writing, the original green block was over here. It replicated and it was stored on data node 3 as well. So the client read it as well from the data node 3 because it is the closest to him, right? And similarly, he'll read the other blocks as well. He'll combine all of the other blocks. Basically, the data nodes will combine all of the other blocks and give him the combined view, and the client will be able to read the data. So this is how storage happens in the HDFS. So let me look at some of the questions that have come up. So one question is by Rupam. He asks, in that case, 3 terabyte files will become about 12 terabyte files with the replication. So not exactly. So here I was talking about only 4 nodes, right? But there can be more nodes. So I actually took a very big size, like a 6 terabyte. So don't particularly think about that. But imagine this: if you have, say, 100 nodes on your big data cluster, which is usually the case for big companies. So you have 100 nodes, right? So in that case, replication does not multiply your data by that much amount. It will still be there across that data. The size will be increased, obviously. So because you're replicating that data, obviously you're also increasing the size of that particular data, but it will not cost your hardware as much because it will be stored evenly across those 100 nodes. It doesn't matter even if you're increasing the size of the data by replicating it. But it is a good question that you asked. That was a good doubt that you had. These 4 data nodes that I have taken here, that they're just an example. That is not the case with actual live cases that you will only have 4 nodes. So in that case, you're obviously costing your hardware too much by storing it almost entirely on the hard drive space of those 4 nodes. You don't have to do that. So one other question: data node have multiple copy to prevent failure, but name node has no. What will happen if the name node fails? The thing is, you can also configure the name node to be multiple as well. So in that case, there's no limitation to how many name nodes you can have. Big companies, obviously, where the data is very sensitive in nature and cannot be lost, obviously there is a backup name node. There will always be a backup name node, and it is impossible for any organization not to have a backup name node. Right? So the data of the name node is also replicated. Don't have to worry about that. One other question: how would the HDFS client number the sequence of the blocks? The HDFS client is a person or a computer at the client's end. So basically what that happens is the name node will essentially tell the HDFS client that you can pick, depending on the latency that the client has with the name nodes. With the data nodes, the name node tells it that you can pick block number 1 from this particular data node. You can pick block number 2 from that particular data node, whichever is the closest to the client. So I hope that resolves that particular doubt. Are there any other technologies that like Hadoop to process big data, or is Hadoop the only solution? There are other solutions as well in today's world. Obviously, there are other solutions, but obviously there is this thing that Hadoop's MapReduce, the processing framework of Hadoop, which we're going to discuss in a moment over here. The processing framework of Hadoop is now outdated. The MapReduce is not used as much anymore. It is used for fundamental concepts, for very custom programs, but it is not used in much frequency anymore. What we still use, though, is the HDFS. We still use technologies based on the HDFS, the Hadoop Distributed File System, for our storage. We do that. So Hadoop is still relevant in that way. We use Hadoop for storage today, very, very frequently. We do use it. What happens if the name node fails? So I have already answered what happens if the name node fails. In this particular case, obviously, if the name node fails, we'll have a lot of problem on our hands. So in a professional environment, we'll always have a backup of the name node as well. We'll have another name node that backs up the data on the first name node. So that is there. We don't actually lose the data of the name node. No way that happens. So let us look at the next slide. So introduction to Spark. So now that we have an introduction to Hadoop, right? So we will have an introduction to Spark. Just a moment. Yeah, introduction to Spark. Apache Spark is it's by Apache again. Hadoop is also by Apache. Spark is also by Apache. So these are essentially technologies that are developed in universities and organizations, and then Apache adopts that particular technology. It becomes open source. So Spark is also an open source framework that has been developed for cluster-based programming. So oftentimes in big data domain, you will see this term being used called cluster-based programming. So this term is based on Hadoop's original idea to combine a lot of computers together, commodity level hardware, very user level hardware, not advanced hardware like servers and everything. Normal computers together to create a cluster in a network and then install Hadoop on top of it. So it was originally developed as an upgrade to Hadoop's MapReduce framework for big data analytics. Hadoop's MapReduce framework, we'll talk about this. So what happened in MapReduce was you had these file blocks present on various data nodes across your cluster. The MapReduce framework essentially took the big data that was there on the respective block, on the respective node, data node. It took it, and then the data was present on the disk. Obviously, the hard drive, the data was present on the hard drive. It took it from the hard drive, put it into the RAM. Then from the RAM, it was then put into the CPU. The CPU processed that data, and then it output that data back into the RAM, and from there it was back into the disk, right? So the problem with this particular approach, right, when you get the desired output, there are a lot of input-output delays. So what does that input-output delay mean? So essentially what that means is that when you transfer data from your hard drive to your RAM, in order for it to be processed by your CPU, there is some latency, there is some delay involved to that. So since you're dealing with big data, right, what you'll often find yourself doing is transferring it from the data from hard drive to RAM and then RAM to hard drive. So what that does is it increases the time in which your processing will happen, right? So this was the case earlier on when RAM used to be really expensive. Like today, RAM is really cheap. You get like 64 GBs of RAM on your mobile phone, right? That is how cheap it has become. Earlier, RAM was really expensive. So we used to have like 2 GB of RAM at maximum on a computer system, right? That was even on the higher side that you had 2 GB of RAM. That was a really extremely good computer, right? So to process this data, we were relying on the hard drive more than the RAM because we used to store all the intermediate information in the processing on the hard drive and then put it back into the RAM. So that caused a lot of input output delays. So as RAM became cheaper, right? So we came up with Apache Spark. It uses a Spark engine for its processing framework, which is the framework engine, the processing engine. The usage of the Spark engine over the traditional MapReduce framework emphasizes on in-memory processing and the shared use of variables across nodes. So this makes Spark about 100 times faster. So what that means is that when you have this huge amount of RAM, like 16 to 64 GBs of RAM on your computer, then you can simply transfer that data from your hard drive once into your RAM. RAM is what memory means, by the way, for those of you who are not familiar. In memory means RAM, right? That is not your hard drive memory. Hard drive means disk memory. In memory means random access memory, right? So this is where the RAM is, right? So you transfer that when you start with your processing job, right? You transfer that data only once from your hard drive to your RAM, and then it stays in the RAM until the job is complete. So all of the information that is created, all of the intermediate data that is created, that is still present in the RAM. The hard drive is not contacted again until the output has been created. When the output has been created, you can surely store it in the hard drive or not, depending on what you want, right? Uh, until the output is created, you don't need to store it back in the hard drive. So this absolutely decreases the input output delay that you would have from transferring the data back and forth from the RAM and hard drive, right? So this makes, in the long run at least, when you have a really big task, when you compare the efficiency of MapReduce and Spark, if you have a really big task, right? Spark is about 100 times faster than MapReduce in that particular case. So that, I hope you understand why that is. So any questions in this particular regard? So there's one question that I can see. Can Spark work on file system that are not HDFS? Yes, Spark is compatible with file systems that are not HDFS. In fact, that is what we're going to be discussing in the next slide. There's one other question. Since Spark works in memory, are there computers with terabytes of memory? No, there are not computers with terabytes of RAM, But if you have like 6 gigabytes to 8 gigabytes of RAM across 100 computers, then across 100 to 1,000 to 500 computers, depending on whatever there is, right? You will have a lot of RAM in collective together, right? So that works for it. And one other doubt that is there, that is a very valid doubt. What if the size of the data is greater than the RAM on that particular node, which is a very viable case, right? So in that case, what happens is you will have a certain percentage of data still present on the hard drive, right? It will still be there. And as much data as you can, you'll put it onto the RAM. You'll process that first, and then you'll take the data from the hard drive and process it later, right? So yes, that increases a little bit of latency, but it's still relatively really fast as compared to MapReduce. Obviously, if you don't have space in your RAM, you'll still have to store that data in the hard drive. That is not a question. If you don't have as big of a cluster, then that will be the case. If you aren't able to divide your data into very small blocks, that would be the case. Yes. What is the minimum RAM requirement for Spark? So it's generally recommended, if you have a large enough cluster, it's generally recommended to have at least 4 gigabytes of RAM, right, on your computer as a data node. As a data node, if your computer is attached to a Hadoop cluster, then it's generally recommended to have 4 gigabytes of RAM to actually be useful in the big data jobs. But you can have lesser RAM as well. There's not a minimum requirement. It'll just be that your data node, your particular data node, will not be as effective. So it will be a bad investment in the first place. So for data nodes, there's not a minimum requirement. Obviously, if you're running a single node cluster, which means you don't have any data nodes, you only have, say, a what do we call it, a name node and data node combined together because you're doing it for practice purposes, then it's recommended to have 8 gigabytes of RAM on your single node system. 8 gigabytes of RAM for practice purposes. So let's look at the next slide. So the topic that comes up is elastic MapReduce on AWS. So usually the traditional way of implementing big data is you have a client and you have a big data cluster, which is a Hadoop cluster, right? You have all of these computers attached together and they are acting as one single unit, which is called the Hadoop cluster. So you remotely access that and then you perform your big data jobs. So this is the traditional way of doing it, offline way of doing it. Essentially, if you're working from office where there is a big data cluster. The other way to do it is using AWS cloud services, right? So there are a lot of advantages associated to cloud services. So the advantages would include you don't have to have an administration team that handles your cluster. You don't have to have a team that installs a new node on your cluster or deletes a node from your cluster. You don't have to have a maintenance team. You can essentially, with AWS Big Data Services, it's just a click of a button. You can create as big of a cluster as you want, containing as many master and data nodes. You can have that big of a cluster. You just have to enter the number in their UI. And secondly, you have the option of auto scaling. So that means that whenever the workload increases and your cluster is not of a good enough size, right? So in that case, you can simply tick on the auto scaling option and the cluster size will increase or decrease automatically depending on the workload. So you can see how easy this makes the entire Hadoop administration process, right? You don't have to have a team, you don't have to pay a team, you don't have to AWS Big Data. It's a managed service. If you have an issue with it, you can simply contact their customer support. So that is the advantage essentially when you're talking about cloud services in general. So AWS is not the only service that provides this, but it's definitely the service with the best features, right? So Microsoft, Azure, and Google Cloud also provides big data services, but with AWS, you'll find that it is the most convenient way to actually use big data clusters. So a lot of big companies use it. A lot of moderate, medium companies also use it. Because who has the time to actually have a cluster in office? Because that's just old today, right? Unless you want really, really low latency jobs. In that case, say big companies like multi-billion-dollar companies, they usually have these big clusters in their campuses themselves. So there's one question, very relevant question, I believe. it means that this will eliminate Hadoop admin jobs in the future. No. So Hadoop admin jobs will always be there because it depends on the use case if you want to use cloud services or not. So say I am sitting in India, right? And I have a Hadoop cluster in the United States. So from India to the United States, whenever I try to contact that cluster, it will take me about 250 milliseconds at an average to ping that server, right? So that is quite a high latency. And say if I am working as a stock market broker, right? That is life or death for me, because 250 milliseconds of delay as a stock market broker can essentially break my trade, right? So when you're trying to analyze a lot of amount of stock market data at once, right, and you want that data to be processed really frequently and really fast, that 250 milliseconds of delay can cause you a lot of money, right? So that is just a stock market example. But if you want low latency, then you will have to install these Hadoop clusters in-house, right? You will have to have the server in-house. You will have to have those commodity hardwares attached in-house. You cannot have them on the cloud, because the cloud will always have latency, because you will never be close to the cloud, which means you will never be close to the Google servers or the Amazon servers or the Microsoft servers. So I hope that answers that doubt. Will not eliminate Hadoop admin jobs in the future, because somewhere somebody is administrating the Hadoop, right? It's not happening automatically. So even in Amazon, somebody is doing that, particularly, although it's automatically handled, but there are issues involved with that as well. So you need to be proficient in admin as well, for those of you who have that admin job. So how does EMR cost compare with Microsoft offering? EMR is cheaper than Microsoft's offering. Amazon is the most flexible with price, actually. I have found personally in my experience, Google Cloud and Microsoft are expensive as compared to Amazon. Amazon also has a lot of options for learners, right? So if you're training, then it also gives you a lot of free tier options. Like you can use one of their EC2 instances and whatnot for free. So Amazon is better in pricing. So while we implement Hadoop in local, do we need of hundred of computers to do it? It depends on your use case. You might need hundreds of computers to do it, or instead of having hundreds of computers specifically for that process, what I mean by hundreds of computers is that you have employees in your office that are in the hundreds, right? You're not actually buying hundreds of computers specifically for your Hadoop cluster. Make sure you understand that. What happens is you have hundreds of computers in your office for your employees. You reserve a certain section of that computer. All of those computers are, by the way, connected to the network together. You reserve a certain section of those computers, right? And that is used for your Hadoop cluster. So the employee will work on whatever he is working on, but a certain section of the computer's computing resources have been used, reserved for the Hadoop cluster. So nobody notices any difference. So that is what it means. So that is what commodity hardware essentially means. The second option for you, especially when hardware has now gotten a lot cheaper, right? You can also have server farms in your office, right? You can have server rooms, which will do the exact same thing. You can install Hadoop on server rooms as well. Earlier, people used to use a lot of commodity hardware as well, because having server farms was a lot expensive. But today, hardware is cheap. You can go for server farms as well. So you have two options essentially, depending on how efficiently you want your job. Obviously, server farms will do it a lot more efficiently. So let us get to the next part. Live workshop. We're going to be analyzing a Facebook pseudo sort of Facebook data set. We're going to be analyzing that with the EMR. So we're just going to run you through the process of that. It's very interesting for those of you who are looking at this for the first time. I was looking for a Facebook logo. Don't mind me. So let me do that. Yeah. So firstly, this is the AWS Management Console. So if you have AWS account, this is how it looks like, right? You have a dashboard and you have a lot of services available to you. So all of these services accomplish different needs. It depends if you want to do machine learning, if you want to run a virtual server for your website, you can do with the EC2, right? What we are concerned with today is EMR. So EMR is Elastic MapReduce. So once you open that, as you can see, I have a lot of clusters that I had opened earlier on as well. So this is how the dashboard for Amazon EMR looks like. So this is used for big data, right? You have a lot of options in this particular case as well. You can create notebooks. Like these will create Jupyter notebooks on top of your EMR, right? So you can simply go into the UI section. You don't even have to look at a terminal screen. You can simply open up a Jupyter notebook and implement your Python code or your Spark code on that terminal using the big data cluster, right? So you have that option as well. So firstly, I'll go to the cluster. I'll click on create cluster, right? So I'll go on. So what is EMR? It is like MapReduce. So it's called Elastic MapReduce, but it does not actually, you don't necessarily have to use MapReduce with it, right? So I'll show you what that exactly means. It's just called Elastic MapReduce. That doesn't mean we're always using MapReduce with it. Yes, EMR can use Hadoop and Spark at the backend. You can no, you cannot. EMR cluster is not free tier. For those of you who are wondering, with Amazon EMR, creating EMR is not free tier. What you can do is create EC2 instances, right? And then you can attach them together and create your. You can just install Hadoop on one EC2 instance, and then you can go ahead. EC2 is free tier. One of the EC2 machines is free tier. You can go with that. Definitely, just I don't think you'll have to pay much if you decide the machine. So I'll just go through this particular option. So I'll just go to advanced options, right? With advanced options, you can select a lot of customizations, right? So firstly, there's the release, the EMR release. So this decides Amazon actually comes up with releases of software packages, right? So currently there are two unstable releases, which are the 6.1.0 and 6.0.0. The current stable release is this particular version, 5.31, right? So we'll go with that. You can then select what softwares you want to install, what frameworks you want to install. Very convenient, right? You can select Hadoop. Obviously, we want to install because Hadoop is obviously going to be there. We're going to be using the HDFS for our purpose, right? And then we have Hive. We don't need Hive for now. We can have you. We don't need you for now. We need the Spark. Let us look at other softwares. We don't need Presto HBase. Yeah, so other than that, we don't need anything, right? So we only need for now, I think, and hope I'm not messing this up. Yeah, so we don't need anything particularly other than the softwares we have currently. If we do need, then I'll have to go again and create the cluster again. All right, so all of the other configurations are correct. So we don't need multiple master nodes. We can say we have the option to have multiple master nodes. For our case, we don't need that because we are only practicing, right? And we have steps which are optional. So steps basically means that if your process has completed, then you can shut down your cluster for the time being so that you're not priced for anything. So you have that option. We're not going to be doing that. We're going to be going slow. We're not going to be adding steps to it, right? So I'll click on next. Then the important part comes up. So we can select our networking settings. So these are related with Amazon security. Very big topic. We don't need to get into that. So here we have cluster nodes and instances, right? So this is where your pricing particular model comes in, right? So in my case, I can select what sort of machine I want to use, right? So as you can see, it does not have free tier machines, but we can see the size and the RAM, right? The GB and the cores that the processor has for each of these machines. So we can select according to our need what sort of machine we want the master node to be, right? So each of these machines are priced differently. You can look at the prices. So you probably wouldn't have to deal with all of this for a training purpose, but when you're dealing with companies and whatnot, so you'll have to look at pricing. And you can see the size of the SSD. So this is a 3.6 terabyte SSD essentially. And you have 768 gigabytes of RAM on one machine. So you can understand how expensive this particular machine would be. So for now, I'm not going to be selecting any custom instances. We're just going to go with the M5X large. And we can go with a core node. We don't need two core nodes. Core node is what a data node is essentially. We'll just go with one, right? And we can see this configuration. We have 16 gigabytes of RAM. We have a volume of 64 GBs, and we have 4 virtual cores. So we'll go with that. And we also have the option for enable cluster scaling. So this basically means that adjust the number of Amazon EC2 instances available to an EMR cluster with this custom automatic scaling policy. So that means that, say your workload suddenly increases and your cluster is not big enough for your workload to be handled in a reasonable amount of time. So in that case, if you have enabled cluster scaling, it will automatically add new instances to your cluster so that your job is done in a reasonable amount of time. When you say MapReduce, is it a synonym for Hadoop? No, it is not a synonym for Hadoop. MapReduce is a processing framework attached to Hadoop. Hadoop has two elements, HDFS and MapReduce. What else AWS services do we need apart from EMR? You can use a lot. You could use Amazon Kinesis. You can use data warehousing tools like you have other tools available to you, Redshift, all of these things. You can use that. Data visualization, a QuickSight. All of this is basically covered in an extensive big data course that we actually provide. All right, I'll call the cluster my cluster. No issues with that. Next, no security settings particularly. I have to give a workshop key as my SSH key pair because I want to connect to my terminal, my master node. So there's a key that I have created already for that, and I'll create the cluster. So this takes some time. Meanwhile, I'll answer any doubts. Also, meanwhile, what I can do is actually put our data set on the S3. So we want to actually access our data set when we run our Spark job. We want to put it somewhere. So I'll put it on workshop practice. Right. So I already have one data set. I'll put another. Click on add file and I'll click on this. So this is the sudo Facebook CSV. So once that is being loaded, I think that has been loaded. Yeah. So I'll click on upload. So is there any specific? So I'll allow public the read access, right? Because I want this to be accessed by my cluster actually. And then I'll click on upload. What is the issue? Okay, so I'll then click on upload. So the file has been uploaded. Yeah. So I'll just keep this address over here. I'll click on the file and I'll keep this particular area assigned on this tab, right? I'll close this tab and I'll go back over here. It's still on starting. PySpark is why is PySpark recommended? It is recommended because of the machine learning libraries. Yes, because Python has a very easy integration with data science, plotting, machine learning, and artificial intelligence technologies. How is data loaded on the EMR? We'll get into that when we actually do our hands-on section. It takes some time for the cluster to actually start because the Hadoop installation is actually happening on both of these clusters as we speak. It's actually slow because you're actually connecting all of the nodes together. It takes a lot of coordination, but it generally does not take a lot of time. It's relatively easy for it to relatively fast compared to the other option that you have, which is actually installing it in house. This particular, when we're dealing with a slow when we're dealing with a low number of instances, it will take around 5 to 6 minutes, 5 minutes at maximum. But when we're dealing with larger workloads, then it can take a larger amount of time. It depends on how many instances are there. So what is EBS and SSD? So the difference between EBS and SSD is that SSD is obviously your solid state drive and EBS is your normal hard drive volume. So it's the difference between the speeds of a hard drive that you have on your computer and a SSD, which is extremely fast writing and reading. All of this is to essentially decrease the latency, nothing else. If you're using SSD, definitely it's faster. Can you SSH into the master and not the name nodes? The master is the name node. So there are two names for it. You can go with master and your core node, which is the first case. You can go with that. The core node is the data node and the master node is the name node. So now the cluster is in running, right? So then now the cluster that is in running, we can simply open up our SSH tool, which is putty. Go and enable an SSH connection. We'll copy the address of the master node, put it over here, right? And then we'll go into SSH. We obviously need our key, right? So we'll go and search for the key, which is the workshop key. think that is the one that I used. Just a moment, I'll check. Is that the one that I used? Yeah, it's workshop key. Okay. Paste it over here, go over here and select workshop key. Go with that, go to tunnels. And then I think there's a port that I have to enter for this to work. So the port is 8157. We go with that 8157. Put that in the source port area. Put this to dynamic because it can change, and we click on open. So we have successfully remotely gotten into our master node, right? So I'll simply go to the change settings and actually increase the font size for a little bit, right? So I'll click on apply. So the guys can see better that way for those of you who have a lower resolution. All right. So the first thing that I would do is obviously start the Spark shell. So the shell by default starts in Scala. It takes some time for the shell to actually start, but when it starts, it's relatively faster. Yeah. So definitely the first thing that I would do is actually create a variable that contains the data set that we have uploaded, right? So the first thing that I would do, and this could be as big of a data set that you want, right? So the S3 currently has a lower size data set. It could be in terabytes, it could be in petabytes, it does not matter. Wherever you're taking your data from, you can simply put in the location and Spark will do it in a fast amount of time, depending on the cluster size that you have. So let us go with a variable creation where we are going to create our data frame. Data frame is something similar to an SQL table, right? So Spark dot read dot format, and the format is a CSV because the file that I had uploaded was a CSV file, right? Put in a dot over here, go to the next line. Option, I want the headers to be included in the column names. The files do have headers. We'll look at how the file looks in a moment. And I want the header to be true because I want the headers. Go another option. And for schema, I want it to be treated like an SQL table, so I'll put this to true as well. Option, and finally fail fast for memory management purposes. And then we want to actually specify the address of the file, so load, and we'll put in the location. So I'll simply go over here and copy the location, the copy path of the file, go back, paste it over here, put in a double quote, and that will create our data frame. So it will take some time. It connects to the S3 bucket and then it imports the file. But once it has imported, it will not take time because then obviously we have it in the RAM. So it took some time, but we have the data set now. So what I'll do now is, for convenience purposes, we're going to be using Spark SQL. So we're going to create a table name for this data frame. We're not going to refer to it as DF. We're going to call it something like FB. Let's call it Facebook for the initials. Let's call it FB. So create a temporary view, create or replace temp view. So this is going to be temporarily the name of the SQL table. So let's call this FB, right? And we do that, put in a double quote over there and press enter. So we have changed the table name to FB for Spark SQL access. It's still DF, but when we're referring to Spark SQL context, it's called FB. So we'll type in spark.sql and let's look at the data set. Select star from FB, which is an SQL statement. So if you're coming from an SQL background, you can understand how simple that makes it for you, right? So you simply have to implement up until here, you have to implement the Scala code or the Python code, and then you can simply go ahead with your SQL knowledge. That is how easy it is. Now you're simply implementing it for big data, right? You're not implementing it for small data on your MySQL. You're implementing it for big data sets. So from FB, and then limit this to like 3 because I don't want my entire screen covered with the data, right? And then I'll simply type in show. Now show is important. If you don't type show, it will not actually give you the output. So some error Okay, I did not spell limit correctly. Just a moment. Yeah. So this is how the table actually looks like, right? So it's a little bit jumbled up. So we'll just look at, there's a user ID for your Facebook ID account number, primary key. You have an age for each of the Facebook users, the friend count of that person, the friendships that the person has actually sent requests for, the person's likes, the likes that person has received, mobile and web browser likes, right? So this is the data set that we have. All right. So let's open that back again and we'll begin with our process. So say I want to find out the number of rows, the number of records that we have in this particular data set. So I'll type in spark.sql, I'll type in select count, and then put in an asterisk over there. So this is simple SQL from now, right? There's no difference between this and SQL. So from FB and put in a double quotes over there and press enter. So I didn't actually type in show, I'll type in show, then press enter. It will evaluate the number of records that are there in the data set, and then it will give me 99,003. So that's the number of records that are present in this particular data set. Obviously, when you're dealing with really big data sets, right, like in the terabytes to petabytes, you will get a lot of records. But the advantage that you'll have in that, it took me some time to actually evaluate this thing, right? And that was because we actually have a two node setup over here, and we're analyzing a really small data set, right? But if you're dealing with a really big data set, what will happen is it will still take the same amount of time as we just took, right? But it'll give us the output. So not necessarily for this, because when we're dealing with a small data set, using a Spark or any other big data framework is not a good idea to use, right? When we're dealing with when we're dealing with a big data set, it still take the same time. So that is the difference there, basically. Right. Okay. So the next thing that we can do is something interesting. We can calculate the average age of a person on Facebook. So spark.sql, put in and select average, it's called AVG. Select AVG and we're going to put in the column name age over there. I think just a moment. So I put an age over there from FB. I think should be in double quotes just a moment. Let's see. So we'll evaluate that. So the average age of an individual on Facebook is about 37, depending on the data set. So these are sort of the questions that you will actually be asked of, the basic level of questions that you will be asked of when you're actually working in the big data domain. So you'll be given a handful of tasks as to what you have to evaluate and visualize and whatnot. So you'll have these data sets available to you, and you'll have to calculate these things and convey this information to, say, the marketing team that you have, the sales team that you have, right? So they can initiate their plans as to how they want to proceed with their business dealings, right? So that is there. Okay, so let us do something interesting. Let us find the average age of a male and then average age of a female and order it by that. Spark.sql, select average age, and then use the column name of gender as well, because we're going to be ordering it by that from FB. And order, I think it's called order, but group by gender, and put it over there and type in dot show. So that will be it will show me the average age of a male and an average age of a female on Facebook. So we have actually three genders. So the one is not disclosed, right? And female and male. So for female, we have 39. For male, we have 35. For not disclosed, we have 74, right? So this tells a lot about not disclosed as well, because we may have some people who have actually entered not disclosed for personal reasons, or we have people who are simply not aware of how that particular aspect works. So let us try something else as well. Spark.sql. Now we can do we do anything essentially. We can analyze anything, particularly for this data set. We can find out something like select average friend count of genders, and then we can simply put in from FB and group it by gender. Put in that and we'll get that answer. So meanwhile that is happening, let us look at what we can do next. So we can see that a female has at an average higher number of friends than the male, which is 165 compared to 241. So we have that with us, that information with us, whatever we want to do with it. And let us now understand the average friends on the age-based demographic, right? So let's go with spark.sql, select average age and average number of likes, maybe. So this is the amount of likes that the person likes received. Let's go with likes received. Received, yeah. So we go with that and go with there from FP, and we can specify where age is greater than equals to 13, which is the minimum age requirement for Facebook. And I think it's yeah, I'm not entirely sure. Is it the and age smaller than equals to, say, let's go with 25, right? So the young generation. We go with that and put it over there and type in dot show, put in there, and okay, so this was an and. I'm pretty sure about that. Select average age and likes received. So is there an issue that we had particularly? Okay. So what exactly did I do wrong over there? Just a moment. Okay, it cannot resolve likes received. So I think I've mismatched the column. It's called likes received. Maybe I have. So I'll just take this, put it up over here. Just a moment. Yeah, so there was a typo. So we can see that the average age of people who are between the age of 14 and 25 is 19. So in the young sort of side on Facebook, we have 19 as the average age, and the likes those persons have received are around the area of 200. So there's that, and you go up and look at something else we can do with that. We can look at friend count, right? And we can also do something interesting with this. We can look at mobile likes, so we can understand their usage, like how many, the usage of mobile phones as compared to web browsers. We can understand that from this. So, firstly, let's go with the friend count. I think we have already dealt with the friend count. Let's go with the mobile likes and the website likes. So let's go with that. Spark.sql, select from average, type in mobile underscore likes, and from FP where age is 13 greater than equal to 13 and age is less than equals to 25. We'll go with that and type in dot show, put it back over there. So what else did we do wrong over here? Unenclosed, we didn't add a double quote over there, so we put that and we get our output. Does it give a squiggly line when the column name is spelled incorrectly? No, it does not. When you're dealing with the terminal is very minimalistic in nature, so you would not get the squiggly line. You will get the squiggly line if you're using some sort of a UI based implementation of it, like you're using a notebook or something. You will get a squiggly line in that. So what are the other questions that we have? Can we access the Spark cluster in any AWS compute engine? So no, you cannot actually do that. You cannot access the Spark cluster, but yeah, you can actually do that. So if you have actually created an EMR cluster and you have a separate sort of compute engine, like an EC2 instance running separately, right? If you have configured the inbound rules correctly, if you have configured the security profiles correctly, and the network subnet correctly, you can actually do that. So you can connect your EC2 instance with the Spark cluster and run these jobs remotely as well. That is also possible. So that is mostly something that is possible. No issues with that. All right. So this is essentially what we can do with that, and we can check the same for higher age demographics, say for greater than 25 and above, essentially 25 and above. Let us see for that. So this is the average mobile usage. If we compare this with the higher age demographic. Let us understand how much activity. Understand this from that the higher age demographic has a generally lower mobile usage than the younger age demographic, right? But we can also check this for website, so web browser, computer. When we do that, we can see that it's 44 for a higher age demographic. And if we simply go ahead and put this back, just a moment, and put this back to www for a younger age demographic, see that it's 55. So we can see that at any age group, the usage of the younger people is higher of social media accounts, social media websites than older people. So that is there. So that is about, I mean, you get the gist of it, right? We can go on and on with creating questions and solving those. But these are the sort of things that you would be actually asked of when you're working in the big data domain. So yeah, there's that. So there's one other question. If you want to create this EMR with just EC2 instances, how do we install Hadoop to use more than one machine? So creating this manually using EC2 instances is very much possible, but it's a very time-taking task, right? So there are a lot of variables attached to it. Hadoop is not that easy to install. That is why there is a Hadoop administrator course, right? It's a very sort of complex thing to do. So yeah, but you can go about and do it. So we're not going to actually go over that in this particular course because I am also not aware of how to do Hadoop administration. Hadoop installation you'll run into a lot of errors essentially when you do that, and you'll have to keep solving them as you move ahead with your job, right? So yeah.
So with that, guys, I thank you all for joining in. Have a great day ahead, and goodbye.